All right, well, welcome everyone to another instance of the Northwest Database Society colloquium. Today, we're super excited to have with us Professor Jun Yang from Duke University. So Jun is actually the Bishop McDermott Family Professor of Computer Science at Duke. He was recently the department chair, so congratulations on finishing that term, very exciting. Yes. He has a PhD from Stanford, and he has broad research interest in databases and data-intensive systems. He has received many awards and recognitions and has had many important roles in our community, including being a trustee of the VLDB Endowment, the general co-chair of SIGMOD 2017, the co-editor-in-chief of PVLDB 22-23, and also has an NSF Career Award, an IBM Faculty Award, HP Lab Innovation Award, Google Faculty Award, and many other awards. So we're super happy to have Jun with us today. Thank you, and we look forward to hearing about your work.
Thank you, Magda. It's great to be here. Thank you for indulging me on this late Thursday afternoon. I know this is not the typical talk slot, and then also I know some of you just came out of that 1 hour and a half long meeting, faculty meeting. So I'll be pretty light on my talk. I have no theorems. I have no algorithm boxes. I have no performance figures. So it should be pretty light, but it's mostly intuition and some of my observations, and it's mostly about how to model the problem as opposed to details about how to solve the problem. So hopefully it will come across as being a nice little afternoon snack for you all. All right. Okay, so the topic of my talk is teaching databases taught me about researching databases. So first of all, how did I get into this business of researching things that are related to teaching? Well, I'm going to start with an observation about database publications. So it's my observation that our introduction section seems to be pretty long. Just wondering, have you ever read a paper that tries so hard to defend that it solves a real problem? Yeah, I see people nodding. Yeah. Have you ever written a paper that tries so hard to defend that it solves a real problem? Definitely. And yet the reviewer number 2 still says, I don't buy it. Where's the motivation? So I been there, done that myself. I tell myself, don't worry too much. We're in academia, right? And graduate students, faculty members, we are at this natural disadvantage because we don't really work with real customers of database systems or database applications, right? And it's hard to come up with really meaningful and real impactful problems and so on. That's what they say, you got to know customers' pain points. But then I realized, wait a minute, I do have customers. It used to be not that many, right? When the computer science major was small, I had like 20-something students in my intro database class. Now I have 300 more in my undergraduate class and 100 more in graduate, of course. So that's a lot of customers. And I talk to these customers in person, right? I know them and I understand their pain points too. Like, they do this. They wait in long lines for my office hours just to get some help, right? And you ask, okay, what kind of help do they want? Well, I teach databases, so you can imagine, as many of you do too, you teach databases or TA for database classes. Well, what is the most common question they ask? Prof, why did you mark this thing wrong? Why is my query wrong? And why did the auto grader, mark this incorrect? Right, so that's the question you get, and you struggle with it. You try to explain to them, and yada yada yada. But imagine doing this for 100 people, 200 people. This is simply just not scalable. So how do you help all these students in a scalable way?
Did you really have to remind me of all my regrade requests I have found in?
There you go. Right. You see, in case you haven't noticed, I'm on what? I'm on slide 4. Okay. I'm done with my introduction. That felt good, I don't like long introductions. So let's just dive right into this problem. So yeah, how do you convince people that their query is wrong? You can provide an explanation, but we all know probably what it comes down to is a concrete example. You tell them, and it's small enough for them to understand it. And I'll also show you an example of doing this. So let's consider our overused database schema consisting of, again, beers and bars and also drinkers. So here you have beers and served at bars, and then you have drinkers who like beers and they frequent bars and so on and so forth. And in this particular homework problem, let's say that the question asks for each beer that Eve likes, find a bar serving it at the highest price. Okay, so here's the correct query, which we call the reference query. Okay, so it's a join between the serves, likes and serves. Okay, you make sure that drinkers like Eve and this is properly joined. And you make sure that this S1 bar, for this S1 bar that you're outputting, there does not exist another S2 bar that serves the same beer that has a higher price, right? That's one of the many ways you can write this query correctly. There doesn't exist another bar that serves this at a higher price, so therefore you're at the highest price. Okay, now somebody comes along and probably they wrote the following wrong query. And this wrong query actually comes up quite often because I've done this for years. I know I spot this instantaneously. It's a three-way join. It's a self join between serves and itself. So S1 and S2 here. Pretend this is the same S1. So it passes the same condition. It's serving a beer that Eve likes. However, here, since I'm just doing a regular join, what happens is that as long as this price is greater than some other bar's serving price for the same beer, I will output S1 bar. So that means it does, of course, output the bar that serves at the highest price, but it also includes some extra tuples, including those that do not serve it at lower price. The only condition, the only tuple that this condition is going to rule out is basically the ones that are at the rock bottom. So if somebody asks me this, I can probably tell them in just 1 minute what's wrong, and I'll make up an example based on this particular mistake to illustrate it. But the same cannot be said for TAs, right? Maybe they're less experienced, they haven't seen this before. Take some time for them to spot a mistake, construct an example, convince the user. And the same cannot be said for some crazy queries that's much more complicated than this one. I oftentimes spend, up to 10, 15 minutes help people figure out, what's wrong with their query. And these are not fun. And by the way, as I mentioned to the students earlier, I have a habit of collecting such queries. So if you ever run into a query you cannot debug or spend so much time to debug, I like to know them. I collect them.
No, you can send them.
All right. So the question is, can I just automate that process I just described that went through my mind automatically in some way and construct this example that serves to illustrate the difference between these two queries, the correct one and the wrong. Now, you might say that, hey, these days, we all use autograders, right? So you already have the test cases. So presumably, people just have to just run these two queries on the test cases and spot the differences and just make the corrections. The only problem is that the test cases are not designed for debugging, probably. They're designed for testing, and sometimes they are, quote unquote, real databases that are moderately large in size. And we're not talking about even very large databases. The largest table that we have in our test instance for this homework, for example, is like 1,200 rows. And of course, this is a database instance that illustrates the difference between the correct query and the wrong query, because this is how the autograder tells that your query is wrong, and students come complaining. But there's really not a very convenient way for them to debug their query on such a database instance. It's still hard for them. It would be really, really nice if you can say, I use a very concise example to precisely pinpoint where the error is and show it to the user. And this is what an experienced teacher would do. And for this particular example, all it takes is basically just an instance with 9 rows. That's all you need, right? So to show this counterexample, we just have to make sure that there's somebody named Eve. And Eve likes this particular beer, American Pale Ale, so APA, let's say. And this beer is served at 3 different places, 3 different bars, and they serve it at different prices. Okay, so on this particular instance of the database, you will see that the correct query would, of course, just return this particular restaurant because it has the price the highest, whereas the incorrect query would return not only just the highest one, but also the second highest because it's not the lowest price. Okay, so this would be a very compelling example, and it's not too difficult for the user to go through and understand what's going on. So
this is also the smallest possible example.
this would also be the smallest possible example. So if you put these last two slides together, right? The previous slide tells us we'll have a large instance where we can already differentiate these two queries. And here is our goal. We want to find a small one. Naturally, you put them together, you have problem definition, which is, okay, given a large database instance, D, where the reference query, the correct one, Q star, produces a different answer from your query or student query, Q. What you want to do is you find a small instance, D prime. Small enough is fine, maybe. Maybe we can even forego this requirement. It has to be the small list. As long as you can find this D prime where this inequality still hold, that's good enough as a counterexample. Okay. So one particular way to make this happen is just to say, let's look at the difference between the correct query and the wrong query. So in this case, it's Q1 minus Q2. You can flip them around. In general, it would be the symmetric difference. Just pick any tuple in the difference. And just make sure that in your selection of D prime, the small counterexample, this T still comes out, right? When you evaluate this difference query in this small counterexample. So this style of explanation is actually very similar to the work from this group, Cosette. Many of you probably have learned of that piece of work. It's very nice, beautiful piece of work that we actually draw a lot of inspiration from. Now, Cosette actually doesn't make use of the existence of some instance that already differentiates the two queries. It just looks at the two queries and try to come up with counterexamples if they are inequivalent. What makes our approach different is we kind of we took a shortcut, or we took the easy way out. By assuming that you have this large instance for which the two queries already differ, we actually make the problem decidable. Because in general, in order to solve what Cosette is trying to solve, you essentially have to detect query equivalence, which in general is undecidable. But for this problem, it's obviously decidable because you already have this big D. In the worst case, just figure out all possible subsets, and you will find one of those, right? So it avoids this theoretical hurdle. And it just works basically for any kind of queries, really. The other thing we kind of cheated is that because you have this underlying instance D, then you don't have to worry about like what values to generate. You can simply just draw subsets of the values from D, right? So that's what makes this problem formulation slightly different from Cosette, but nonetheless, there are some techniques that are very similar. So how do you go about solving this problem? It's quite straightforward, but I promise you I'm not going to give you any algorithm boxes. So I'm just going to sort of walk through the intuition a little bit. So suppose that you're interested in just making up some D prime to come up with a case where this difference that exists in D still shows up in D prime. What you do is you basically trace this tuple that's in the difference between these two queries back to the base table rows through its provenance, and try to figure out the minimum number of input rows that's needed to still support this particular row's derivation in this difference. Okay, so here's one example just to illustrate a high-level idea. So if you look at the same example here, this is the wrong query, and it has this extra tuple here, right? So we're going to try to basically make a test instance that still makes this show up in Q. So how do we do that? That's our T, and we look at the provenance of this tuple in this particular query. Remember, that's a join query. It will basically try to say, if you want to derive this particular output row, you need another S2 bar that basically serves this the price of the beer at a lower price than this one, right? So in order to support derivation of T, you have to at least pick another bar that's serving APA at a lower price. Now, in your actual database instance, there could be multiple of those, but as long as you pick one of those, you will basically have T in Q. Okay, so that's only one part. The other part you have to make sure that is that T does not accidentally just bump into Q2, right? So for that, you have to look at your correct query, and you want to make sure that this T, because we're modifying the base instance, we want to make sure that modification does not lead to T all of a sudden being put inside the result of Q2. because that would make them indifferentiable on B prime. So what do we do? How do we do this? We again trace the provenance of this tuple T back to its input rows, and using this time using Q star. But of course, T is not currently in the output, so it's only a potential answer. There's a way to trace the provenance of potential answers or possible answers through the input too. And in this case, remember there's a not exists query. What it turns out is that the provenance through Q star will tell you that, okay, if you want to make sure this T comes up, then you better make sure that you pick none of the bars serving APA at a higher price because of that not exist condition in that correct query. Okay. Now you don't want this to happen, so you have to negate this, which means that in order for T not to show up, you have to pick some of the bars that serves APA at a higher price. Now, if you combine these two together, you basically get a following condition. You have to pick one bar that's serving APA at a higher price than this one, and pick another bar that's serving the price lower than this one. And that's exactly what our counterexample was, how it was constructed. So that's the basic idea. So through some provenance tricks, you can actually construct an example instance where you can differentiate these two queries. Okay, so that's the high level idea. There's some interesting variations of this problem. If you look at basically the properties of Q1 and Q2, you will notice that if Q2 happens to be monotone, then in fact, this problem can be solved by totally ignoring Q2 altogether. Because all you have to do is to make sure that in the instance T prime, T belongs to Q1, right? And the fact that this Q2 is monotone means that as long as T, since we already know that T does not belong to Q2 on the larger instance, it cannot possibly belong to a smaller instance, right? So that's an interesting variation that simplifies the problem a lot for some instances. If you want to general, yes.
Just one question. So then maybe this is on the previous slide, just in general. So if a student wants to use the system and comes with a query and they're like, I don't understand why it doesn't work. Do you show the, do you just generate the smallest instance between their query and the solution query?
That's correct.
But then you only show them the instance?
We only show them the instance, but we also show them which tuple should not be or should be in the result.
It's up to them to figure out how to
That's
make
correct.
a query.
That's correct. Yes.
So
Yes.
help me understand something about the provenance. So it's easy to imagine queries with few something like exists or these quantifiers.
Yeah,
But
yeah.
the provenance is everything in the column, right?
That's right.
Is this,
That's right.
and so how do you reduce?
Yeah, so there are some tricks that we use to reduce basically computational provenance. So one of the things, the most obvious optimization that we do is that we're not trying to trace everything. Here we kind of say, if you're willing to give up the overall guarantee that we pick the overall smallest counterexample, then our goal is to just give me one tuple. I just need to differentiate, just look at if I want to keep this one tuple in the difference, what's the best I can do? So that way you don't have to compute provenance for all the results, right, in your query. You just have to focus on this particular one. And you can push down the properties of this particular tuple to the provenance evaluation to get basically smaller results. But in general, I agree with you. It could be a long expression, right? If you have things like non-exist and lots of things match with this particular condition and so on. Yeah. But the point is that we don't have to compute the whole query provenance, right? You can focus on one tuple.
Okay. Maybe what I'm imagining is an example where you say, if the sum of this column is this exact number,
Okay.
right?
I have a slide for that. That's the next slide.
I'll leave you to it.
Yeah, that's a very, very good question. That's a very good question. We have to modify the problem definition again in that case. Yeah. Okay, so there's another variation which is more general, which is, okay, here we just care about like preserving one tuple, this T. I want to reduce D to D prime and still have this T come out. But you can also ask the question of, what if I want to preserve all the answers? Right, so in this case, the Q would be like difference query in general. You give a query, and you want this query to produce all its results. But can you make the input database as small as possible? That's a very nice general problem. And So there's a recent ICDT paper in 2024, just won the best paper in ICDT. And it's actually from two former members of our group at Duke, Xiao and Stavros. Now, I have nothing to do with this particular paper, but I'm still very proud of them and proud of the fact that this problem gave them a little motivation to work on this larger problem. Now, back to your question. There is some gotcha, right? So this very beautiful, nice problem formulation doesn't always work when it comes to some more complex query patterns. So some, in this case, I use average as an example. So here my query is computing for each beer, basically the average price. Now, this is a tall order if you insist that the same tuple T comes out when I reduce my input size, right? Because here you have to essentially make sure that the subset of the prices you pick still somehow magically generates the same average price as if you preserve the entire subset. That's just, it's too much, right? So we really have to relax this problem definition to say that as long as in D prime, the query results are different, then you're good. You don't have to really preserve the same difference tuple in the result. The other case is even more troubling. It's not even happening by chance. It just basically says you cannot have a small counterexample, right? So this is an example when you have a group by and you make sure that this particular group you're returning has to have a membership count of more than 1,000. Then no matter what you do, you have to make sure that this particular member, this particular group has more than 1,000 tuples. So there's no way to have any size, any database instance size smaller than that. So that obviously would not make our approach work because we wouldn't have a small counterexample for students to debug on. So we have to tweak. In reality, we have to tweak the problem definitions. Instead of insisting on getting the exact same result tuple back, we allow it to be different. And also, we allow you to tweak the queries as well. So in this particular case, the observation is that, hey, if this query works for 1,000, it probably should work for greater than 3 as well. So we might as well show you a counterexample and say, well, that's a counterexample for count star greater than 3. And for that one, I can manage because the count is reduced. This does not always work in some corner cases. I'm not even going into the details, but we'll be happy to talk more. Okay. So I'm not going to delve on this particular problem too much, but I'll quickly say that all this has been implemented and has been deployed at Duke. We love this system as teachers and teaching assistants because the counterexamples don't reveal the correct solution query. So students cannot copy from it because you only show the result of the solution query in some sense over this small counterexample. But they don't get to see the query itself. They see the result of it. And also the counterexample doesn't reveal the full test instance. So you're not giving your full test instance away. It's always just a small subset of it. Now, of course, some students could reverse engineer by some smart way the entire test database. But in that case, I'll give him full credit or her full credit. Now, for students, they love this too. Why? Because it's almost like an infinite supply of counterexamples, right? As long as they're failing the autograder, our technique will come up with some counterexample they can debug on and resolve that difference and move on. If they have another mistake, the process will repeat. So it's basically just, you can keep doing it until you get it right. So this stuff is reported in this pretty old paper now in 2019. And we also had the demo in the same conference. I would just share some highlights from the evaluation, not too much. This is back at the time when we still did not have such a high enrollment, like 300, but still 170. So in this particular evaluation, we basically put RA-test the system live and release it to all the students. They can choose to do it. They may choose not to do it. It's totally voluntary. We tell them this might be helpful for this homework. Okay, and we will only release it for subset of the problem, not all, so we can have some comparison points. And we looked at basically the correlation between the usage of RA-test and also the homework scores, right? And we do see that, hey, they clearly improved performance on hard ones. On the easy ones, everybody got just perfect score in the end. We couldn't get any signal out of it, but for the hard ones, definitely. So one concern with this approach, because it's not very controlled environment, you're asking people to sort of voluntarily use RA test or not is basically the self-selection bias, right? It could be that people who choose to use RA test, they're just better students or more motivated students, then they will score higher. But there are things we left in the design that allow us to basically tease out additional information to conclude that it's not just self-selection bias. So in particular, in this case, we had 3 hard problems that we were interested in. So H, I, and J. So this problem I is the one that we released RA test for. But H and J, we had no help, no additional help from our debugging tool. Also, J is not so much related to I, whereas H is actually quite similar to I, with just some small variations. Now, what's interesting is that, of course, first of all, RA test usage improved the performance of students on I. Okay. It also improved the performance on H, just because it's similar. That's our explanation, at least. But it did not improve the performance on J at all. Right. So if it's all self-selecting bias, you would have expect that, maybe on J, you would see the adopters of RA test probably will perform higher than the other group. But in this case, just nothing, right? They really did not derive any benefit. So that's one way to basically take what data we have and then try to, see if self-selection bias played a huge role or not. Now, of course, without a controlled environment, we cannot really say for sure. But at least we can say that it's not all because of self-selection bias. Yeah.
Is it not surprising that there's no difference on J? To me, it's more surprising than if there was a small difference. Because all the students who are motivated are going to use the tool.
That's right.
And then the students who are not motivated.
Oh, so you're thinking about the reverse case where maybe students who are going to do well, they will not use the tool.
No, sorry, let me say it
Okay.
More clearly.
Yeah.
The students who are motivated to find resources to help.
Yeah.
Right?
Yeah.
Which will be the students who opted in.
Correct.
Well, they can't use this tool for this problem.
Right.
Right? You might expect they would go to office hours. Right?
Okay, yeah, that's a perfectly legitimate answer. Yeah. That's another interpretation.
A small difference to be in J and not in.
Yeah, you're right. Yeah, so maybe we should have looked, but anyway. Yeah, the data is what it is.
I think there's assumption here is that students who are motivated tend to use the RA test, which might not exactly be true, I think. So for example, I would imagine some students might want to, in order to get a higher grade, so
Right.
he or she will just keep testing with autograder until, let's say, fix some error to get like higher grade, but just might not be that motivated to solve another question, I guess. I'm not sure the reason.
So I'm actually not surprised though, because the motivated students, they will do well whether they chose to use RA test or not. Some of them maybe chose, some other ones went to office hours. Like motivated students will just get the top grades on all the assignments, period. But then what happens is in the regular setting, you have students who are less motivated and they just don't get top grades on all the assignments. So I'm not surprised, and that's what I would expect, that some of them used RA test.
Mhm.
Maybe that was a lower bar. You don't have to talk to anyone. You don't have to leave your dorm room, right?
That's quite that's quite possible as well. I think the way we set it up, there's basically no way to tell what exactly is at play here. You really need a much more controlled experiment to really tease out what is really making a difference here. Yeah.
But it sounds like some problems had the tool available and some did not. So you could do a within subject design where you can see for that same student, are they doing better on equivalent problems or not when they have the tool versus not have the tool?
I think so.
That's right. So between H and I, we could look more closely. Yeah, we did not, but we should. That makes a lot of sense. Right. Yeah. Thank you for that suggestion. That makes a lot of sense. Anyway, so so this is basically one adventure into the user study that we had for RA test. We also had just more qualitative feedbacks. So we had the anonymous survey right after we deployed RA test and asked them various questions. Most people wanted to have more of it. And we were very glad to find out that at least 70% thought that it helped debugging because this is a pretty high bar. Primarily, this counterexamples can illustrate you have something wrong in your query, but they don't necessarily lead to a fix immediately. But nonetheless, 70% of the people found it very useful. We had another question that just asked about a particular question, whether to help convince you that your query is wrong and understand why it's wrong. And that has a much higher yes answer rate. It's about 90%. Okay. And there are some words that students put in their feedback, largely positive with some constructive feedbacks and so on. So some of this we've incorporated in the later versions of RA test, but this RA test has been used since the fall of 2018. So by many iterations of the classes, and people now swear by it. So it's benefited more than 1,600 students. Now students will, used to be, they will complain about, why does this class teach about relational algebra? It just seems so, random and maybe not useful as SQL and so on. But now with our test, they say, oh, we teach relational algebra, we get to learn about it. We actually are not afraid of debugging a relational algebra. So that was nice. So there's some other issues that we worked on following this RA test work. We looked at these concrete examples and still did not like them completely because if you look at it, it's still very verbose, right? There are certain pieces of information that are not really contributing to understanding the mistake of their query. So for example, like, why do I care that Eve lives on this magic way? It's not relevant to understanding the mistake. So is there a way that we can actually reduce these kind of useless information? And also the other thing is that it doesn't highlight like where exactly the problem is. If you were to highlight it yourself, you probably look at this pattern here. You have like 3 prices in this particular sequence. And it's the fact that you have these 3 different prices that lead to the difference in the answers. Yet here, there's just basically 3 numbers. It actually takes some more effort to figure it out. It's their relationships that actually makes the query break. So are there ways to basically get rid of some of these details? Can we abstract the essence of this counterexample in some way to help debugging more? And also, what if there's no test instance to begin with? So to answer these questions, we extended this work to abstract instances. So the idea is that instead of giving you the concrete values, we're going to use these variables, right? So and don't care. So like address, it doesn't really matter. You can plug in any constant here. It doesn't really contribute to whether this query is wrong or right. Drinker 1 is a named variable, and then make sure that drinker 1 actually likes this beer 1. Okay, and this beer 1 is actually served by these 3 bars. And also for these 3 prices, they have to satisfy this condition: price 1 less than price 2 and less than price 3 in order to be a valid counterexample. So I present this entire thing with basically instances populated by variables and don't cares, plus some global condition. I give this abstract instance to the user. It just helps highlight what exactly the problem is and get rid of some distracting details. Yeah.
I spend a lot of time preparing slides for students who are not computer scientists. They need to learn databases. And I spend a lot of time thinking about a slide like this. How would I present it? And I wouldn't present it exactly like this, but you definitely ask the right question. For example, for price, I find it more informative to put here like 10, 20, 30. I think it's faster to see, you don't need to look up and see if they're all the relation. You get a point. But don't put 275 and 325.
Right. You want
something that's easy to pass. For a drinker, I would order that Alice or Bob. Give me a name so I know this is a
concrete value. Yeah.
And then bar 1, bar 2, bar 3, I think they're great. But these are choices that I make subjectively. But your talk suggests maybe there is an automated way to make these choices. And
yeah, we could. Yeah, we could. Actually, Dan, you just beat me to another slide. I'm going to actually mention it. We did some user study on this. It totally confirmed what you say. Okay, totally confirm what you say. But anyway, just to conclude this slide, we basically extended some techniques, concepts from the incomplete database literature, in particular, V tables and then C tables, And in order to make this abstract instance, we call them C instances. But in any case, oh, the other thing that we did in this extension is that we also try to answer the question of, given the query, can I produce all possible C instances? Well, let me put it this way. Can I produce C instances that would satisfy this query, make this query return something in all possible ways, by some definition of all possible ways? Because a query could be satisfied in multiple different ways, right? If you have disjunction, for example, one thing happens, then something will be in the result. Another thing happens, something else will be in the result. I want to try to explore all these possible ways that a query satisfies. So in the context of debugging would be, if I look at the difference between the two queries, I want to expose all possible ways that the difference can manifest itself. So if I can do that and present all these C instances, it will basically illustrate all the mistakes in a query, as opposed to just one, right? Because our previous approach just picks one of those types. And then we thought this would be great. So we did some user study and see, okay, do you like abstract instances? And we test your performance using the abstract instances versus the concrete instance. And guess what? Actually, abstract instances actually worked better. They actually spotted more mistakes compared with concrete instances. But you ask them what they prefer, they pick the concrete instances. So and maybe it's not surprising. It really conforms your observation. And it's but I strongly believe that they need to be taught to think in a more abstract way. And hopefully I'll have some chance to come back to this particular issue, because we're going to build on this instances as a building block to address some of the issues, like, for example, verifying if a query is correct. And I think some abstraction there, instead of the concrete instances, will be tremendously helpful. But there is hope. So in the same user study, we actually look at just the graduate students versus the undergraduate students. The graduate students are more receptive to the abstract instances. So I think this is this skill can be taught. So there is hope. All right. Yeah.
Question about interpreting this study.
Okay.
In my mind, there's two possible interpretations. One is students prefer concrete instances to abstract ones.
Yeah.
But another interpretation is students prefer to have one mistake pointed out at a time as compared to all the mistakes pointed out at them. Do you agree?
Yes, I would agree with that. Yeah, I would agree with that.
And these are kind of two questions that can be asked separately.
Yeah. I mean, ideally, I think it can be asked separately. I have to look back at our survey questions and see whether there are whether it allows us to actually tease that out or not. I don't think we just basically, let's see. Yeah, you're right. I think we just presented the C instances, two of them at the same time, and that may actually be interpreted a little differently.
I see this with students, sometimes we get query that's so wrong, right?
Right.
And if you told the student all the ways it's wrong,
It confuses them. Yeah, you're right. Yeah. Yeah, I mean, user study is hard.
One question. So
yeah.
how do you handle when, let's say if you have a query that has multiple subqueries?
Mhm.
Because then there could be, maybe that's to the point of there could be like errors in different subqueries, or
Right.
the student won't know, since you have, like, they want to know which subquery might be. So of course, good students will know to, like, okay, I'm going to do one subquery at a time.
Yeah.
But do you provide any other special help or anything?
So we do have, so the next piece of the talk I'm going to talk about is a little similar to this idea, where we would look at the cases where a query may have multiple issues, and how do we basically repair this one step at a time.
Okay.
So coming up, next slide. All right. Okay, next slide. So far we're trying to convince people that their query is wrong. They have some understanding why their query is wrong, but the next question they're asking, how do I actually fix my query? Right? So what are the actionable fix? So here's, again, a pair of examples, same database schema, but slightly different queries. And this will help illustrate some of the gotchas when you're trying to do this type of thing, trying to provide hints. So this query is trying to find, for each beer that Amy likes, rank the bars she frequents serving this beer according to the serving price. Okay, and just to make things a little simpler, we assume no ties here. So what the correct query is trying to do is basically does this join. You join together one copy of serves and another copy of serves. And you make sure that S1's price is less than or equal to S2's price. And when you group on S1, you're basically counting how many things are greater than or equal to this particular certain price, right? So that will give you the rank. And again, I'm assuming that the ties. And in the end, you maybe have a having condition, you group by drinkers and all that. You have a having condition that restrict this entire query to just Amy. Anything before this, it's actually solving a more general problem. It's for each beer that an individual likes, then you do this. Okay, it's probably this is supplied by a mathematician, this sample query, because they like to solve the general problem first and then just basically apply a filter at the end. But the run query does something different. The run query here basically also does this serves do a soft join. Obviously, it misses the frequency table. So this one is not too hard to spot. But then things get a little interesting, right? Because here you have this where clause having this drinker equals to Amy. The correct query doesn't have that. But that doesn't mean that this is wrong. You shouldn't prompt the user to correct it because this basically achieves the same effect. You can push this selection condition down through the aggregation. Okay. The other one that's tricky, well, I guess I'm skipping this line too. I mean, these two conditions are actually not exactly the same, but by transitivity equality, that's not too hard to detect. The next one is a little trickier. So if you look at these two, it's S1 price less than or equal to S2 price. This one is S1 price greater than S2 price. Maybe you're prompted to think that, oh, you have to change this greater than to less than or equal to. But that will be a very, very misleading fix. Because if you read these two queries carefully, you will see that the user actually intends the row of S2 here to be the row of S1 in the first query. It's just that they are used differently, even though their name happen to be named similarly, it doesn't mean that they serve the same row. So the correct fix should actually just add an equal to here. That's the only case that they missed. Right? You know, there are many other things that you can see that are different, but really not important, and so on and so forth. So what I'm trying to say with this is that there are many, many different ways to write a correct reference query. There's not a single correct solution, right, in terms of the syntax. So you cannot really just rely on the syntax to suggest fixes. On the other hand, you cannot completely ignore how the run query is written, right? Because this reflects the student's thought process. So the right way to fix it is to say, okay, let's work with your query and try to fix it. Instead of saying, I can't figure out what's wrong, why don't you just do the sample solution thing? Which, you know, I'm afraid sometimes we have to do just because the queue is so long. But ideally, you really want to start from their query and try to fix it because that gives them the best experience. The other point I will point out, and this is one that we actually struggled for a long time implicitly in our mind, is that really, if you think about it, there's no easy way to say any part of the query is definitely wrong. Because in logic and in querying, you can always kind of make things correct later on by doing some compensation. Right? So for example, if in the correct query you see a greater than or equal to 0, and in the incorrect query you see a greater than 0, it doesn't mean this has to be incorrect. Well, what do you mean by incorrect? There actually exists another correct query that contains this so-called incorrect predicate as part of it. So it's actually missing this part as opposed to this one is wrong. And there are many other instances where you cannot really pinpoint where the mistake is. And we made the initial mistake that, oh yeah, you go for hinting the mistakes. And then we realized we can't even define what a mistake is. So we switched this problem definition to, okay, forget about identifying mistakes. Just figure out how to fix it, right? So focus on finding repairs that make things equivalent instead of saying something has to be wrong. So now we can have the problem definition. Okay, so here's your reference query. That's the correct one. And here's your incorrect query. Okay, they look very different. And it's probably not a good idea for you to nudge the user to that direction because that will completely change the way that the user has been thinking about this query. What you really need to do is look at the set of all the queries that are equivalent to the reference query, no matter how different they look in syntax. And then you pick the one that's syntactically closest to the run query. And you say, we nudge the user to that direction, right? So really the problem definition comes down informally to finding the cheapest repair to this query, run query queue, such that it becomes semantically equivalent to the original query queue style. Yeah.
No question. So When you say that you want to make the queue semantically equivalent to queue star, so is it also assumed that this will work only on a particular database instance, like?
No,
that's given?
in general,
In general.
in general. So it's not possible, right? It's undecidable. And you guys are so good. You always anticipate what will show next. So that's a great question. But this immediately implies we have to solve the query equivalence problem, right? Because at least in the cases where equivalent, you need to detect the edit distance is 0. There's no repair to suggest. So in general, this is pretty hard to do. That's one.
Another question, so here going to go on the, no, sorry, you're going to look at the query, so to look at the distance to repair it, you're looking at the query plan or at the SQL?
We're looking at the syntax, yeah. So some representation of syntax tree of the SQL, and we define this distance to be the edit distance, right? Some version of the edit distance.
Because I wonder if that would be, because I'm just wondering, in some cases, there might be something that maybe syntactically is longer, but if you compare the query plans, like just the logical direct translation might be actually simpler, but maybe there's no such counterexample.
Yeah, so I think you can, I mean, in general, you can use the logical plan as a surrogate for some kind of distance measure, right? So you could imagine maybe the distance between the logical plans.
As opposed to the SQL.
Yeah, so it's sort of somewhere in between. But the thing is that there are many logical plans that are equivalent too. So it's very hard to, we're back to sort of square one, right? You need to detect whether logical plans are equivalent.
Right, no, but I mean, you just kind of want to go to the same, like you fix it, right, to go to the correct, closest.
Right, so you're saying basically, think of them like, nudge them in terms of in the logical plan space.
Exactly, right, but it might be, but I'm just wondering because sometimes you can like add a subquery or something, and maybe something like that might actually look like a big syntactic difference because of the keywords.
I agree.
Maybe actually just one operator somewhere.
Right. I think that as an intermediate representation may be better for the syntax tree in terms of figuring out the difference between the two queries semantically. In some sense, we prefer the syntactic distance because that's the most intuitive for the student to understand. Yeah.
That's a good point.
So,
the student doesn't see the.
Exactly. So that you have to kind of introduce another way of explaining what you're trying to nudge them to. Yeah. So another issue, which comes back to an earlier point you raised, is that if many times they have multiple issues in them, and it's not clear in this problem definition, how do we even manage that? Like, how do you present all those mistakes at the same time? So this formulation doesn't really try to address that. So we took a more practical approach. Definitely want to dodge the bullet in terms of undecidability. So we're going to try to hint and repair stage by stage. Okay, so think of this queue as your working query. You're modifying it as you go, and you have to clear each stage by passing a particular check, a viability check. And once you pass that, you get to move on and move on to the next stage. So this validity check is actually sets an explainable goal to the student that, oh, we're trying to do this. So for example, in the case of the from stage, we're basically trying to make sure that your query actually gets data from the right table in the first place. Otherwise, all bets are off, right? So that will be, in a sense, your viability check for passing the from stage. And then you move on to the where stage, where you try to make sure that your query considers all the correct subsets of input row combinations in your final output. And the group by will make sure that the partitioning of these combinations of rows are the same between you and the correct query and so on. So not only do these conditions set explainable goal, it also ensures that you're constantly making progress towards the eventual correctness. So at the end of the stage, what we promise is that, hey, there exists some query that conforms to your query based on all the previous stages, and that is actually equivalent to your target, okay? So that means you can keep going. You don't have to revisit an earlier step to fix things again. So you're not going to go in cycles. So this is what ensures progress. Yes.
So does this approach miss a case where you had earlier where like having Amy in the heavy condition and in the web?
Great question. So even though the students is progressing from one stage to the next in a very localized way, the system underneath it is doing the look ahead. right? So when I'm hunting a student's query in terms of what to fix in where, it's actually looking ahead at, okay, in the correct query, I have that having over there. So this where clause is actually not incorrect, right? So yes, so when we're making decisions of what to suggest, it does look ahead beyond these stages or other parts of the syntax. Okay. So for this particular example, if you run our system, it should just basically give you two hints. The first hint will mention that, okay, frequency is required. You don't have it. You don't have to give this directly to the student. What we envision is that this is a tool actually for the TAs. You give it to the TAs. TAs takes a look, knows exactly what the problem is, but they can like, frame the problem in a different way that requires some more thinking on the part of the student. Assuming that student has correctly added this new table and linking all the right conditions, and assuming those are correct, then the where stage would only prompt this particular fix. And it's the correct fix where it just changes the greater than to greater than or equal to, and it would like omit all those false positives and so on. And again, the TA can rephrase it in a way such that it's not so obvious as a hint to the user. Okay, so I guess I don't have too much time left, but there's just one particular. Okay, maybe we have a choice. I can go on and talk about several other projects that are related to education, or I can dive into this one particular problem a little more. Any preference?
What are you more excited about?
Huh?
What are you more excited?
Okay, then I'll just go with the flow. Let me just do a little more. Yeah, okay. So there's a lot of interesting things that goes in fixing each of the stages. So I'm going to share just one stage with you. Again, no algorithm boxes and so on. It's mostly just about problem definition. So let's just focus on fixing the where clause. Okay. And here assume that the previous problem of fixing the from clause has been solved. So we know that we're joining the same subset of tables. And also we assume that we have to figure out the table mapping. Oh, this table variable versus that table variable, they refer to the same one. So you can basically unify all these where conditions together, they use the same variables. Now you can just pretend you have two Boolean predicates, P from the wrong query, P star from the correct query. Okay, and they're not equivalent right now, but you want to basically find smallest repair to P such that it becomes logically equivalent to P star. So let me pare down this even a little more. Let's say that you only get to touch one part of this P, right? So here's the syntax tree of P, and we say it's only this one little block. Somewhere down here you can touch. The rest you cannot change, right? How would you make basically P equivalent to P star? Okay. Now you can write it out. Okay, so P is probably some combination of P1, P2, Pi, and so on with X, which is the part that you want to repair. You can swap it out with anything else. And this has to be logically equivalent to P star. This awfully looks like an equation to you, right? You can kind of solve for X, if you will. So it's interesting to think about it this way. There could be no solution. In other words, no matter what you plug in here, this will never happen just because of these other PIs in there. Okay, and we have a very simple check for this. Or it could be the case that it exists a set of fixes, and these set of fixes happen to fall into a range that's bounded by a lower bound and upper bound condition, such that any fix that falls in between this logically, so L of X implies L, and further implies the upper bound for X. Anything that falls in between will work as a solution. Okay, and we also have a simple procedure to compute this bound. So why is this the case? Again, just some intuition, it's not a proof. So pretend this is the problem that we have. This is your target. Okay, what you have is basically X and Q. So this is your Venn diagram. Yeah, so this is the part that's covered by Q. This is the part that you want to cover eventually as the correct query. So how do you make that happen? By choosing some value for X. Now, obviously, you can choose X to be just precisely this. So when you add it together, it gives you exactly P star. But you could also pick X to be this whole thing. Am I right? And that whole thing is intuitively P star or not Q. the reason why this works is that once you take the conjunction between X and Q, this part gets clipped out by Q, leaving just P star, right? And also this one would also work, right? This is this rectangle. And in fact, anything between that lower bound, which is P star, and this upper bound, P star or not Q, would work. So basically all the solutions fall into this particular range. It's just some intuition here, one concrete example, but if you're interested in the proof, you can check the paper. Okay, so, but we haven't completely solved the problem yet. We have an optimization problem, right? We're now having established that this X falls into this bound. You have to basically pick the simplest X. So what is that simplest X? So here, let me convert that Venn diagram to something a little more concrete. Let's say we have this space of all possible tuples. It has two columns, A and B. The range is basically 0 to 4 for both of those. So Q is this half space, yeah, A less than 2, right? And P star is basically this rectangle has 4 sides, and each side corresponds to one of these atomic predicates. So what happens here, you see, is the space, you can think of it as partitioned by these half spaces. Each one of them corresponds to one of these atomic predicates. Okay, and you want to look for an X that's in between the lower bound and upper bound. But the lower bound is nothing but some polyhedron that's bounded by these half spaces. And the upper bound is also some shape that's bounded by these half spaces. Right, so you're looking for a shape that's sandwiched in between that has the lowest complexity. In this particular case, it would be how many sides, or yeah, because it's two-dimensional, how many sides it has. And that would be this one, because it has 3 sides. As opposed to, say, for example, P star would have 4 sides. Right, and that's exactly what's missing here. It's a trivial example here, but hopefully you kind of see the point. Now, if the solution doesn't come out for you, maybe one more slide, endure with me, we'll basically make the solution completely obvious to you. So here's what we're going to do. We're going to think of this X that we're trying to solve as basically a Boolean function, right? Where each of these variables is basically one of those atomic predicates. And 1 being inside this particular half space, 0 being outside of particular half space. Each partition of this space, the smallest indivisible unit, is actually basic. If you think about constructing a truth table for X, then each of these partitions will basically be a row in the truth table. It's a mean term, which is determined by whether this particular partition is covered by each of these half spaces or not. Okay. So basically, having a lower bound of Lx means that for any partition containing Lx, X has to be set to 1. So, sorry, I skipped 1. So this has to be 1. And then for anything that's outside of the upper bound, they have to be set to 0, right? For anything in between, they're basically don't care. You can pick or not pick. Now, this ought to look like some exercise from your introduction to architecture, right? This is basically logic minimization, right? So you can basically apply espresso or something like that. Now, I'm running out of time, so I'm just gonna sort of skip many of the remaining challenges. So there are many other interesting problems that are in other stages of doing this repair, then you can check out in the paper. This is going to be coming out very soon. Okay, so I think I'm going to skip all the way, all the way. But I want to just, if you will indulge me with one additional ongoing work, I want to go back to that point about abstract instances and why we need them. So we're looking at this problem, we're working with generative AI that produces SQL queries. The biggest problem is how do you debug these queries? And so how do you do that? The scenario we're thinking about is basically the user has in mind some queries that they want to answer. They don't know how to describe it in SQL. Okay, and generative AI comes up with a candidate query. And our system basically asks a sequence of questions to the user. It will get some answer back, and such that you can use these answers to prove or disprove the correctness of Q. So again, examples come to help. So you can use concrete examples, make up some concrete example, show the result of this generative AI query and see if this result is what's intended by the user. And the user may say no, then you immediately know that this query does not work. But what if the user says yes on any questions you pose to it on a concrete instance? Well, unless you make a lot of constraints on what kind of queries you can write, you're not going to be able to say much because it doesn't generalize. Right? Where we think the key is, we have to go back to those abstract instances. So if we allow these oracles that are to be issued to the users, we ask them to check on this abstract instance whether the generative AI query returns the correct result. We have something to build on because this is a general statement. So we can actually construct a proof of correctness from it. Okay, conclusion. I'm sorry, I'm out of time. So overall, I've just presented just a very small sample of a number of research problems we're tackling that's related to teaching databases. It's been very meaningful and fun for me. Meaningful because students are actually important customers because they are our future, right? And it's fun because it does give us a lot of research problems, not just sort of for CS education research problems, but also disciplinary problems. And what I especially liked is it naturally forces us to think about taking approaches that are very explainable to the users, which is a very important thing now that we have more and more black box stuff coming. So if you're interested in using any of the tools that I mentioned in this talk, please get into touch, right? So if you're teaching 344, 444, or 544, and thinking about running some of these, tools or automated testers, get in touch. I'm willing to put in some personal time to help make it happen. Okay, so with that, thank you again.
So let's start with the